Okay, hi everyone. So let us continue with our, hello. Let us continue with our floating point, and hopefully we can finish it today. So we talked about floating format, right? We said we have half precision 16-bit, single precision 32 bits, and then double, which is 64. And in this module, we are looking at the 32 bits, single precision. Then we said this is the format that it follows. Here, exponent has, we have to be careful about it because we have a stored one. We have a stored exponent, and then we have what the actual one is, okay? And even though floating point is always a signed number, it's showing a signed number, all of its components, all of its parts are unsigned binary bits, basically, okay? The sign is basically unsigned. Fraction is UQ23, and then exponent is also an unsigned one because we are adding a bias to it. So here, the actual one is the stored exponent minus bias. Okay. The other, and then with the exponent having 255 levels, we can, as you can assume, we can show very large numbers and very small ones. But that's not the only feature of the floating point. The other thing is, instead of just simply saying underflow happened, overflow happened, we have cases that are special. For example, you can differentiate between if positive or negative zero happened. And you can see that this is good if you are trying to say, okay, if you should be producing a plus infinity or minus infinity. The other special case is subnormal. Okay. Remember we said, let me just go back to it 1 second. We said exponent, when we were showing you the actual range of exponents, we said it starts from 1 and ends from 254, right? Remember that? Here. The stored one goes from 1 to 254, right? For the 32-bit, which is 2 less than 256 levels that you can have with 8 bits, because 0 and FF are reserved for special cases. So as soon as you see 0 in the exponent and or 0 or FF you see in the exponent, then you shouldn't be treating it with this format. This format is no longer true for these special cases. Okay? So if this stored exponent is 0, then it's either actual 0, plus or minus, or it's subnormal, depending on if the fraction is 0 or not. Makes sense, right? Exponent is 0, and then fraction is 0, so it's 0. But as you can see, it's not following this formula, because if exponent was 0, it would be 2 to the power of minus 27, and then f would be 0, which would be 1. So this format is no longer true for these cases. Then for subnormal. For subnormal, we cap this exponent to minus 126. Again, this format is not correct, because if the exponent was 0 here, it should have been 2 to the power of minus 27, right? But for subnormal, it's always capped to the minus 126, and then the format is going to be 0.f. Okay? That allows us to have this subnormal underflow that is happening gradually. You know, the difference between 2 to the power of minus 27, 127, which was the smallest value that we could have shown with normal floating points. Instead of going from 2 to the power of minus 127 to 0 immediately and then underflow, we are doing that gradually. And that's the impact of subnormals. So we have a better handle on very small numbers. It allows us to actually cover, let's go from this side, 1.18 multiplied by 10 to the power of minus 38, and this is in decimal, to 10 to the power of minus 45, basically. So we got a range there by the subnormals. Then we have infinity when all the exponents are 1 and the fraction is 0. If we have the exponent to be 1 all the way and the fraction is non-zero, then that's nan. Nan meaning that not a valid answer or something like that. Okay? If you want to get more details, we have something called quiet nan that can propagate through your code, and then a non-quiet one, basically, a significant one, or signaling nan. But this is beyond the scope. But you can even differentiate between what type of nan is happening and keep track of it. So floating point gives you this option too. Any questions? Good. So whenever you see exponent to be all 0 or all 1, you are not following this format anymore. It's a special case. It means it has a different meaning. Okay? Just be careful about that one. Okay. Now let's go to some arithmetic on floating point. We learned how to convert floating point to decimal and the other way around. Now let's try to add them up, multiply them. Okay? So here I have two numbers. Each of them are represented or can be represented in the floating point format. So number 1 is minus 1 to the power of S1, 1 F1, multiplied by 2 to the power of E1. And then number 2 is S2, 1 F2 to the power of E2. When you're adding together, just like if you were adding, let's say, 1.43 to 330.5, you had to match the decimal point, right? Here you have to match the exponent as well. For example, to do this, you would add a 0 here and match the decimal points and then add them, right? You would never add them like this. You would never add them like this. So here, the same idea. What we are doing is we are matching the exponents first, and then we are continuing. Then, if both of them are positive or negative, you're adding them up. You're adding. Mentisa here is, M1 is, if you remember, 1.F1 or 1 plus F1. And then M2 is 1.F2 or 1 plus point F2. So remember that when you're adding, you have to add that implied 1 to them. Okay? So bring that into your calculation. Then we normalize result so that, we are again we are coming back to the floating point format. And then we are checking for exceptions. And if it's all good, then we go ahead with the representation. Okay? Let's see this in an example. We have minus 42 plus 0.75. Okay? Let's go through decimal conversion to, floating point once more, and then we continue with the operation. I brought my cheat sheet. So, minus 42. What was the first bit in FP32? What was the first bit? Sign. Thank you. And what is the sign here? Sign bit here? 1. So we have 1. And then what do we have? Should I be even starting? It's minus 42. Should I be starting putting the bits together? I have to normalize it first, right? Okay, so let's take a step back. Okay, so let's do first normalize this, okay? Minus 42 over which number? 32, 2 to the power of pi, multiplied by 2 to the power of 5. And that is going to be minus 3125, 10 2 to the power of 5. Perfect. So this means in FP32, this is going to be 1 for the sign bit. And then we have the exponent. What should I store for the exponent? What is the exponent?
132.
132, thank you. So the exponent is 5 plus 127. It's 132, and it is going to be 1, 0, 0, 0, 0. How many zeros do I have? Okay, 4, 5, 6, 7. Okay, there was 5 of them. It's 128 plus 4, right? So, and this has to be 8 bits for the exponent. Now it's fraction time. Fraction, you can either do it like, how do we want to do it? It's 0.3125. You can see this is in UQ 23. So in order to convert it is 0.3125 multiplied by 2 to the power of 23. And that is going to be some number that you can present with 0101. And then continue this till you get 23 bits. And this is our fraction. Now let's do plus 75. Actually, I think it was you. You asked last time, how do we present 0.5 in floating point, right? No? Oh, somebody asked, anyway. So if the number is less than 1, what should I do? How do I normalize it? Go ahead.
You multiply by like 2 to the power negative.
Yes, you multiply it first, right, to bring it above 1, and then you divide it. So this is going to be 1.5 divided by 2 multiplied by 2 to the power of minus 1.
So
it's going to be, I said it exactly reversed. So it's going to be 0.75 multiplied by 2 over 2. Or, again, you can say this is multiplied by 2 to the power of minus 1. So they cancel each other out. This is going to be 1.5, 2 to the power of minus 1. So you probably already know this. So let's go. What is the first bit? 0. Then what should I look at? What am I storing next? What am I storing next? Anybody wants to answer? They can raise their hand. Go ahead.
126.
126. The exponent that I'm storing is 126. Okay, then what I'm doing? Okay, so the exponent 126, how do I show it? Okay, it's 0. Let me keep the colors. 5, 6, 7, 8. Okay, 8 bits. Then you know 0.5. How do I show 0.5? It's the fraction is 0.5. In UQ23, how do I show that? What's that?
First one and then all zeros.
Yes, exactly. Remember, the point is kind of like here. So 1, 0, 0, 0. Perfect. So now I got the two of them together. Now we have to align the exponents. So step 1, aligning the exponents. Step 1. How do I do that? So minus 42, because it has the larger exponent, this stays like minus 1. This is how it will look like. 0, 1, 0, 1. The rest of it is just 0 to the power of 5, right? This is basically what we have. What did I do to show? This is the fractional part of 42. I added the implied 1. I added the sign. And then the real exponent that I had, the actual exponent, multiplied by 2 to the power of 5. Then 0.75, we have to bring it to this one. 0.75 was 1.5 to the power of minus 1. In order to bring it to 2 multiplied by 2 to the power of 5, I have to multiply it by 2 to the power of minus 5, right? So you shift it left or right? So it's going to be even a smaller number, right? So it's going to shift right. So it's going to be 0. Before it was 0.1, or sorry. 1.1, don't forget the implied one, but now it's going to be 0, 0, 0, 0, 4, right? Or 5? 5. Yes, 5. 1. Yeah. 1. Then oh, sorry, I made a mistake. So this is 1.100000, 2 to the power of minus 1. If I want to bring it to 2 to the power of 5, I shift everything 5 points, or 6 points. Somebody help me. 6 points, right? Yeah, 6 points. So 1, 2, 3, 4, 5, 1, 1, I think. Five now. Go ahead.
How can we shift the one that's like outside the fraction? Isn't that one the one that we add to the binary? Can we
Yes.
shift that one as well?
So imagine you're bringing 1.5, right? Think of it this way. You're trying to write 1.5 in a smaller, or you're trying to say 1.5 multiplied by 2 to the power of minus 5 multiplied to when you're doing this, if it was 10, what would you do? You would just do this, right? So okay, let me just make sure that I got this correctly. So we had plus 0, 0, 0, 0. I really have 5, yeah. Zero, 1, 1. Okay. Now that they're matched, we go to step 2. Okay. So what do? We can do subtraction, right? So subtracting now, what we're doing is we are subtracting this one from this one. 0, 0 should be like this. 0, 0. And that is going to be minus 1.0100. Zero one zero zero one. So we have minus 1 0 1 1. I think it's going to be 0 1 1, something like that. And then the rest of it is just zeros to the power of 5. So since the result is already normalized, we don't have to do anything, okay? So the next thing we do is step 3 is that we are showing minus for the sign. And then what we are storing here is, so we are going to store 1 for the sign bit, which is minus. And then the exponent is 5 again. So it's 5 plus 127, which is 132. Is going to be 1 0 0 0 0 1 0 0 1 2 3 4 5 6 7 8 9. That's wrong. This is the exponent part, and then for the fractional part is going to be, again we remove the implied 1, and it's going to be 0 1. 0 0 1 0 1 1. The rest of it is 0 0. All of it is 0. I think so. So if we look at the result, minus 41.25, okay, here, let's see if we got that correctly. You double check this actually, because we still have multiplication to cover. But yeah, the important part in the addition, here in the floating point actually, because you have to match the exponents, the addition is more challenging than multiplication. Multiplication was harder in the fixed point, but here it's reverse. Okay, in multiplication, easy. The signs are going to be, you're going to get XOR, meaning that if they're the same, it's going to be positive. If they're different, it's going to be negative, right? And then the exponents are going to add up, But the important part is to bring it back to the range of the exponent that you wanted to keep, okay? So either here, I'm going to tell you here, either add actual components, exponents, actual exponent 1 plus actual exponent 2, and then for the actual one, you would add 127, and then this would be your stored exponent. If you're doing the multiplication using the stored exponents, remember that you have two 127 hidden in it, right? So it's going to be a stored exponent 1 plus stored exponent 2 minus 127. Just remove one bias. Because both of them have biases in them, you're removing one of the biases. And then here, again, we are multiplying mantises here, which is basically 1 F1, 1 F2. You're not multiplying the fractions alone. Just like you're multiplying the real numbers. The real numbers have an implied 1 point in them. And then if you have to, you can, let's say you're multiplying 1.5 by 1.5. That is going to be 2.25, right? You have to normalize it back. So after you do this step, if you have to normalize it, then you do normalization. Then the rest of it is the same. So let's look at it in this example. Again, we're going to do minus 42 multiplied by 0.75. So we found that minus 42 is 1, 1, 0, 0, 0. And 0, zeros minus 0.75 is going to be 0, 2, 3, 4, 5, 6, 7. Zero. Okay. So sine 1, S1, I'm going to, is 1. Exponent 1, E stored 1, let's say, is 132. And then F1, or 1.F1 is 1.0101. The rest of it is just 0. S2 here is 0. And then E stored 2 is 126. 1F2 is going to be 1.1000. Okay. Following the steps, the sign of the multiplication is going to be S1 XOR S2, which is going to be what? 1 XOR 0, 1. Yes, it's going to be a negative number. You're multiplying a negative by positive, it's going to be negative. Then E stored. It's better to do E stored because then you don't have to do the addition. But here it's going to be 132 plus 126 minus 127, which is going to be 131. Right? Perfect. Then we need the mantissa thingy. So that's going to be M. And then that is 1.0101 multiplied by 1.100. So this is where that, the binary arithmetic, the first lecture we started with in this module, it's very helpful because now you're multiplying two binary numbers basically. Okay, so all you need to do is that the first row is going to be 0, 1, 0, 1, all zeros. And then the next one, you're multiplying by the 0.1. right? So you only need to shift it once. The rest of it is 0. Now, if you do this, it's going to be 1, 0, 1, 1, 1, 1, 1, right? I think so. Yes, I did it right. Do I have to normalize this? No, perfect. It's already normalized. Now, I want to do this. So I'm going to say S. E is stored, and then the rest of it is M minus 1, basically. M minus 1. So it's going to be 1. 131 is 128 plus 3. 1, 2, 3, 4, 5, 6, 7, 8. And then the rest of this, I'm dropping the 1. I'm only keeping the fraction part. So this is going to be the result. Okay? And that is going to be, you can confirm and see if you can convert this back and see if it's 1 minus 31.5 or not. Hopefully it is. Looks strange. Yeah, okay. Any questions? Yes.
Can we go to the addition example?
Mm-hmm.
When you add the 0.75, should there be like 5 zeros before the leading one? In addition?
5 zeros? Isn't there 5 of
On
them?
the right you have 5, I think in the sum.
Oh, yes, you're right. That's why it looked weird. It looked different. You're right. Thank you. So what I had was this one, right? I'm shifting it. 1, 0, 0, 0, 0, 0, 1. But is that correct? Shouldn't it shift 6 times? I feel like it should shift 6.
I think that is 6 because the leading one, the 1 point on the left becomes the leading.
Oh yeah, that is correct. Yeah. Yes. So 5, and then I have to have a 1 here. Is that correct now?
I think so.
Okay. So then we are subtracting here, and yeah, this number, I don't think this is correct anymore. 1, 0, 1. Yeah, this is not correct. Let me see. Oh, by the way, have I shown you the website for FP32? No, right? Okay, so there is a website, a calculator for FP32. When you're practicing for your exams or your project, if you need to double check, you can use that one. It's called IEEE. Let me just write it here. IEEE. Yes, this is very helpful, and then you can use this one. So what I'm going to do is that so I'm adding I'm subtracting. Zero, zero. Can actually somebody do this? It's minus 41. Okay, let's see if we get that. So here I have 1, 1, 0, 0, 0, 0. That's correct. Then I have 1. Okay, so this is wrong. This is going to be 1. Zero, 1, 0, 0, 1, 0, 1. Okay, I think I got it this time correctly. But yeah, double check it because I realized that my answer had a problem, so I had to correct this here. Okay. So now, why do we care about floating point? Floating point, as I said, it allows you to get range. Okay. Are you still with me? Okay. It allows us to get ranges, and it expands on the application. But it comes with a price. It consumes more power. It occupies more cheap area. And then, more importantly, beyond all of this, you would need special hardware for it. Because without that hardware, as we said, fixed point is much faster. It's better to use fixed point if you don't have the hardware than using floating point. So if you don't have to, right, it's always better to use fixed point. If you don't need the range of the floating point, don't use floating point. Especially always check that your chip or whatever your board has a floating point hardware. Okay? For example, in lab 3, what you're doing is that you can manually disable the hardware FP unit that you have, FPU. Okay, so you're going to disable it, and then what it's going to do, by default, it's going to go to the software way of handling floating point, and you see it's much slower, right? It's even slower than fixed point. But once you have that hardware, you pay that price, yes, of course you get something in return. Okay, but yeah, avoid it especially if you have a low power application. So I already told you all of this. Then, something else you might notice is that a lot of arithmetic operations that you would do, they're not as straightforward in floating point because, for example, here adding A and B, doing this addition and then adding them to C is different than, the error is going to be even different than adding A to this summation of B and C. I think on Piazza maybe somebody was talking about variance calculation and they were like, why is it like, was it you? Why is my error different? Well, because different operations they have, and then going back to the standard formats means differently when you're doing the division first or the addition first. Okay, so it's not non-trivial, but like you should know that different operations and bringing back to different standards at each level means a different error, truncation error. So just keep that in mind. And sometimes it is important if you are trying to minimize that error to see which operation you should be doing first, right? Which math you should be doing first. For example, here, the Kerbal Space Program, it says like, you know, the spacecraft drifts due to the floating point precision loss, because it's that important. Or Minecraft if you played. So, similar issues. Yes. Yeah, your world would corrupt at large coordinates in Minecraft if you do that. Okay, then we talked about the fact that, you know, you can have beyond IEEE 754. What they're called mini float, and they're used mostly in machine learning and accelerating AI, especially in new chips from NVIDIA. You would see these being used. We have brain floating point, which is bfloat 16. And here we have 8 exponents. Half precision, the regular FP16 had 5 exponents, right? But here we have 8. And then we have FP8, FP4 even. And then again, it's just low precision, but fast operation. Here, in your STM32, what you have is the single precision one, not double precision. You have FP32, not the FP64. And then what else? And as I said, you can manually roll back to software, floating point software, and you would play with that in your lab 3. What else? The block diagrams of FP hardware, it includes registering files, multiplier, adder, you know, because once you have those components, then the operation would take 1 cycle as opposed to hundreds of, you know, cycle times. Yep. So this is it on floating point. If you have questions, ask. But that's it. On the logistics part, I'm gonna stop. Does anybody have a question on floating point? No? Okay. So remember, I put a document floating point versus fixed point. Please, if you can, study that. Okay, and we are not going to cover it in class, but it will make things easier for you to understand if you follow that.